Okay, guys, so for the next week, we are going to explore lots of different techniques to being able to factor algebraic expressions. And so in our previous lesson, we looked at factoring by looking for the greatest common factor, okay? And so whenever you're given an expression, that's the first technique you always want to go for. Okay. You always want to look to see if there's a greatest common factor in each of the terms. So, for example, let's say you had 2x squared plus 6x. Okay. There's two different terms. There's 2x squared and there's 6x. So what you do is you look for factors that they have in common. So I look at 2 and I look at 6 and say, what can I divide into both? Well, I could divide both of them by a 2. And then you look at the variables. Okay, you have two factors of x in the left term and one factor of x in the last term. So how many x's can you take um, equally from both? Okay, equally, you can only take one. Okay, so after you identify what the greatest common factor is, here the greatest common factor is 2x. What you do is you pull it out of the expression. Okay, we say pull it out of the expression. Um, and, and it kind of feels like you're taking it out, right? Whenever we distribute, whenever we multiply, it feels like we're putting it into it, all right, multiplying it into the expression. Here we're going to be taking it out. And so what will we be left with after we divide? Well, 2 divided by 2 is 1, and x squared divided by x is just x. Plus 6x divided by 2x, well, 6 divided by 2 is 3, okay? And then x divided by x is 1. So you're left with the factored form, 2x times the quantity x plus 3. Okay, but with factoring, it's kind of like whenever we simplified our fractions, you always have to make sure you factor your expressions all the way. So after you're done looking for the greatest common factor, maybe there's one you can factor out, maybe there's not. You want to continue to look and see if there's any more factoring you can do by using our techniques, okay? So this is a factoring web, they call it, okay? And it's kind of a map to show you how to do this. And so we're always going to start up top and we're going to first look for the greatest common factor, okay? After that, which technique we're going to use, we're going to learn 4 different techniques, okay? And which technique we're going to use is based on how many terms are left inside of your parentheses, okay? So we're going to look at our first method today called the differences of squares. So this factoring will work when you have 2 terms, okay? Let's go ahead and start looking at our notes. Okay, so to introduce factoring the differences of squares, first I want to look at what it looked like whenever we distributed, okay? So whenever we were factoring the greatest common factor, whenever we were distributing going the opposite way, we were always distributing one term inside of a parentheses. But multiplication got more complicated because sometimes you had multiple terms in both sets of the parentheses. So you had to multiply every single term by every single term. So to go in reverse and pull that out is going to be more complicated. So that's why we have so many different techniques to being able to do this. So as a warm up, let's go ahead and simplify these polynomials, okay? And then we'll work on what it looks like to write them in their factored form. So right now it's in its factored form, x plus 4 times the quantity x minus 4. So when we distribute, you have to make sure you multiply everything by everything, okay? Some of us like to use FOIL, okay, if we are doing a binomial times a binomial. So x times x is x squared. 4 times, or x times negative 4 is negative 4x. 4 times x is a positive 4x, and 4 times negative 4 is a negative 16. Combine these like terms, they actually end up going away, and you have x squared minus 16. Okay, for our next example, 5m times 5m is 25m squared. 5m times negative 1 is a negative 5m. 1 times 5m is 5m. 1 times negative 1 is negative 1. So we combine these two like terms, and they actually end up going away. I'm seeing a pattern here. If you notice, look at these set of binomials, okay? Whenever we talked about distributing, um, these binomials actually have a name, okay? And I think I mentioned it to you. Whenever you have two binomials and the only thing that's different between them is the sign, right? Here, this one's a plus and this one's a minus, but everything else is the same. Equally the same here, okay? And the same here. These binomials have a name. They're called the conjugates, okay? They're called conjugates of each other. And so what's really cool about conjugates is when you multiply them together, that middle term, the single variable term, goes away. So in the first one, the x term went away, okay? You still had the x squared term, okay? That's different, but the term that just has the single x goes away. Same here with the m, it just ended up going away. So can you guess what's going to happen here? Yeah, they're just going to go away. So we have, let's multiply it out and see. 2a times 2a is 4a squared. 2a times negative 3a is negative 6ab. 3b times 2a is a positive 6. I always write in alphabetical order, ab. And then positive 3b times negative 3b is negative 9b squared. Those end up going away. Shocker. 4a squared minus 9b squared. Now, not only do I see a pattern on this side, but I see a pattern on this side too, okay? What are some of the things that I see? Well, I noticed that they all have two terms, right? 1, 2. This one has two terms. This one has two terms. So they all have two terms. I also noticed that they're all subtraction. Okay. I also noticed that they're all subtraction. And what I also see is that each term is a perfect square. And maybe that one was a little bit harder to see, but we'll explore it here in a minute. So that brings us to our first term. How do you take something like this and then rewrite it into its factored form? Okay, and so these types of terms, I'm going to give them a name because we found some very solid characteristics about these guys. I am going to call them the differences of squares. Okay, the difference of squares. And so remember, the difference is a subtraction problem. So when you're subtracting two terms of squares. That means that each one of these terms is a perfect square. Okay. So let's go ahead and look at the steps to solving these. So first, we want to make sure that we actually have the differences of squares, okay? So step one, look at your expression, and you have to make sure you have the differences of squares. And there's a few things you need to consider. First, you need to make sure that there's two terms, okay? You also need to make sure that it's a subtraction. Okay, and then you also need to make sure that each term is a square, a perfect square. Okay, and sometimes this third guy will take a little bit of work to be able to say for sure. Okay, so that's what step one looks like. You have to make sure there's two terms and that there's a subtraction sign in between and that you can express both of them as a perfect square. Okay, then we're going to use the following rule. So we have a squared minus b squared. So let's say that that's our polynomial or our expression. What is that going to look like? It's going to factor into two binomials. Okay, it's going to factor into two binomials. And so what is that going to look like, those binomials? Well, remember this guy and this guy and this guy is going to look something very similar, right? One of them has a plus sign and one of them has a minus sign. Now, all we're going to have to do is once we identify what our terms are here, okay, what our bases are, we're going to take those bases and we're going to fill them in. We're going to write the A here and the B there, and we'll write the A there and the B there. So it's going to feel like when we're factoring, all we're doing is kind of just filling in missing pieces and we're done. As always, you will be able to check your work by distributing to see if you get the expression, the original expression back. So I'm going to go ahead and save those examples for the next video.